Hello and welcome to today's video where we shall be discussing two special types of topologies, the discrete and indiscrete topologies. In our first video, we had defined and explained in details what a topology is. Let us quickly refresh our memories on the definition of a topology. Definition: let X be a non-empty set and let tau be the collection of subsets of X. Tau is said to be a topology on X if 1. The set and the empty set are elements of tau. 2. The union of any number of sets in tau belong to tau. And 3. The intersection of any two sets in tau belong to tau. Then, the pair X tau is now called a topological space. I advise you watch the first video to get a full explanation to what a topology is. Now, what is a discrete topology? Definition: let X be any non-empty set and let tau be the collection of all subsets of X. The keyword here is all. All subsets of X. This is the keyword all. Then tau is called the discrete topology on the set X. And then the pair X tau is called a discrete topological space. Now, if you recall in the definition of topology, we said that let tau be the collection of subsets, not necessarily all the subsets. So when tau becomes the collection of all subsets of X, then tau is now called a discrete topology. Let us give an example to illustrate what we are saying. Example: let X be set with elements A, B, C, and tau the collection with the open sets X, phi, A, B, C, AB, BC, and CA. Question is tau, this collection, a topology on X? Let us check. Now to check this, what do? We check if the collection tau satisfies the three conditions of the definition of a topology. First condition is that X, the set, and the empty set must be elements of the collection tau. Let us check if that is true. So X is it element of tau? Let us see. In tau, is there X? There is X. And the empty set is an element of tau. The empty set is here again, an element of tau. So the first condition for a topology is true. We now check for the second condition. Second says that the union of any number of sets in tau must belong to tau. So if we take any two unions of open sets here, let us see what happens. Let us take any arbitrary ones. We'll take B and C, for example. B union C. And the union of these two open sets gives us BC. And is BC an element of tau? Let us check. Yes, BC is an element of tau. So BC belongs to tau. Let us try another two pair. Let us take AB and BC, for example, again. If we take the open set AB union the open set BC, what will be the result? AB union BC is simply ABC. Now, is the open set ABC in tau? Let us check. ABC is nothing but what? The entire set itself, X, and X is in tau. So ABC is in tau. Let us take one more union. Let us take AB and CA. Let us take AB union the open set C and A. And what would that be? That would be ABC again. And ABC belongs to tau. As a matter of fact, any two unions you pick here will always give you an open set in tau. So we can say that the second condition of a topology is true for the topology tau. We now check for the third condition. The third condition says that the intersection of any two sets in tau must belong to tau. Let us see. Let us work with this open set here. For the first one, open set B intersection C. Now the intersection is what? Is empty. There's nothing in common. And is empty a member of tau? The answer is yes. The empty set is a member of tau. So that is true. If we intersect the open set AB and BC, what do we get? AB and BC B is common. And is B an element of the collection tau? We check. Yes, B is in tau. B is in tau. Let us take the third one here. AB intersection CA. And what will it be? AB and CA. A is common. Is A a member of tau? We check. Yes, A is a member of tau. A is a member of tau. As a matter of fact, if you pick any other two open sets in tau and check the intersection rather, you observe that the intersection is also an open set in tau. Therefore, we can say that the collection tau is a topology on X. And if that is true, it therefore means that the pair X and tau is what? A topological what? Space. But what do we observe? We do observe that this collection tau has 1, 2, 3, 4, 5, 6, 7, 8 open sets. And these open sets are all the subsets that can be obtained from the set X. Recall from your power set P of X that the power set of a set is equal to what? 2 raised to the power what? N elements. That is to say, if a set has n elements, then the set will have 2 raised to the power n what? Subsets. In this case, X is ABC. So here, n is equal to what? 3. So how many subsets will set X have? It will have 2 raised to the power 3 equal to what? 8. So it will have 8 subsets. So we now see that the power set of this set X has 8 subsets in it. And the 8 subsets is what we have here for tau. If you recall our definition of discrete topology, we said that let X be any non-empty set and let tau be the collection of all subsets of X. And if that happens, we say that tau is a discrete topology on X. That is exactly what has happened here. We have verified that this collection tau, defined this way, is what? A topology on X. In addition, we have also observed that the collection tau is actually the collection of all the subsets from set X. So, this makes tau not only a topology, but what? A discrete what? Topology. But a discrete what? Topology. And if tau is a discrete topology, it means that the topological space X tau is also what? A discrete topological what? Space. At this point, I make the following remark. And it is this, that the discrete topology is the largest topology you can have from a particular what? Space. Because it contains what? The subset of all elements in X. So the discrete topology is the largest topology. Now we look at the indiscrete topology. Definition. Let X be any non-empty set and tau be equal to the collection X and phi. X and phi. Then tau is called the indiscrete topology. And the pair X tau is called the indiscrete topological word space. What do we observe here? We observe that for an indiscrete topology, the collection tau is made up of only 2 open sets, the set itself and of course the empty set. Let us construct an example to illustrate what this really means. Example. Let X be the set with element, just one element 1, a singleton set. And let our collection tau be defined as X and phi. Question is tau a topology on X? So we have to verify the conditions for a topology. The first being that X must be an element of tau. Let us check. See tau. Is X in tau? Yes. X is an element of tau. Second one that says that phi must also be an element of tau. Is phi in tau? Yes. Phi is an element of tau. So the first condition is checked. Second one says that if we take any union of 2 open sets in tau, the result should also be in tau. And in this case, tau has just 2 open sets. So we now check the union of X and phi. If you take the union of a set and an empty set, the result is what? The set itself. Is X in tau? Yes, X is in tau. So the second condition for topology is also checked. The third one talks of intersection. If we intersect X and phi, what do we get? The answer is phi, empty set. Is the empty set a member of tau? The answer again is yes, since the empty set is in tau. So we can check the third condition again. So we conclude here that since the three conditions of a topology have been fulfilled, we conclude that tau, the collection tau, is a topology on what? On the non-empty set what? X. The question now is this: what type of topology is it? If you recall our definition of the indiscrete topology, we say that the collection tau must be an open set with just two, must be a collection with two open sets, X and phi alone. Looking at our example here, X is a set, a singleton set 1 with element 1, and tau contains just X and what? The empty set itself. So, since the collection tau on X is just X and phi, and we have verified that tau is what? A topology on X. It therefore means that tau is now called a what? Is called rather an indiscrete what? Topology. And just like we had remarked earlier, that the discrete topology is the largest topology, that exists. The indiscrete topology, on the other hand, is the smallest. Is the smallest topology that exists, and it's also called the trivial topology. Also called what? The trivial topology. So what it means is that for every non-empty set given to us, the smallest topology that set can have is the set itself and what? The empty set. I hope you understand what we have done so far today. And of course, X here and tau is called the indiscrete topological what? Space. Leave a comment and subscribe to this channel. Thank you and bye-bye.